Good afternoon. I'm Riccardo, PhD student at the Department of Mathematics of University of Namur. And today I will talk to you about self-organizing dynamics in complex systems on non-normal networks. Before I start, I would like to thank the organizers for giving me the opportunity to present my work. Exactly 3 years ago at BENet in Ghent, I presented for the first time ever as a master's student. So it's really nice to be back here, even though we are not physically in Ghent. We are in a bit a particular setting, but still it's really nice to be here. And so in our group, we study dynamical systems on networks, in particular how the network topology affects the behavior of the system. So let us take a dynamical, let us consider a dynamical system, a variable evolving in time due to a certain law given by a nonlinear function. Nonlinear because usually interesting phenomena happens when functions are nonlinear. And then our topology is discrete, is on a network. So we have this dynamical system on every node. But this system is without space, so we need a term to account of the space. And here we have our coupling term, where A is the adjacency matrix of the network, while G is the function of the coupling. So on every node, now we have these dynamical systems, which we have the dynamics of the variable plus the part due to space, which may have some effects on the overall dynamics. To study this kind of systems, a very useful tool is the master stability function. It is a numerical method developed by two American physicists, Pecora and Carroll, in the late 90s. And it computes for each value of the coupling the maximum Lyapunov exponent. Here we show an example for the Rössler oscillator. So a 3-species dynamical system. Here we have diffusing coupling. We chose this system for this example in a chaotic regime. So the master stability function for the uncoupled system, when the coupling is 0, the Lyapunov exponent is positive. That's why is positive. And then we have a part that is negative. So the system, after it's perturbed, remains in the state it was before. And then when it's positive, the system goes unstable. Our topology is discrete. So also our master stability function will be discrete. And now you can see already that changing the network, we can change the behavior of the system. For example, if I choose a network whose coupling is different, like this one, we have a case where all the eigenvalues, all the master stability function, except of the uncoupled one who doesn't affect our analysis, are negative. So from being unstable, the system goes stable. And we didn't change the dynamics, we just changed the topology. And for every toy model, Gisborne-Landau, Fitz-Nagumo, Volterra, Lawrence, and many others, you can find in the literature many different plots of the master stability function. That is, so maybe they have different names depending if it's a fixed point, a limit cycle, a chaotic system, but it's always the maximum Lyapunov exponent as a function of the coupling. The toy model that we study is the Brusselator model. That is also the only Belgian model because it was developed in Brussels by Prigogine and Nicolis. It's a 2-species system having 2 possible regimes: a stable fixed point, and in this case, the framework in which we work is called Turing pattern formation, or a stable limit cycle, and the framework in which we work is called synchronization. The dynamics that we study is synchronization. And this system is usually, and especially by us, studied with diffusive coupling. So the Turing pattern formation we have a stable equilibrium, and after perturbation, the diffusion may activate, so is activated and may bring the system to be unstable, leading the system to a new stable state that is a pattern. So you can see here that you have inhomogeneous concentration of this chemical in this petri dish. And in fact, it was studied first in the framework, it was proposed in the framework of morphogenesis and then studied in chemistry for chemical reactions, the framework in which the brusellator was developed, and it is used to explain, for example, the coats of animals, the leopard, the fish, also the patterns that we see in vegetation or in shells, and so on. And then this theory was generalized about 10 years ago on networks. It is the one we are interested. So here the objective, you have a stable state, is to have instability. In the framework of synchronization, a theory that is much older, developed by Dutch physicist Christian Huygens, we're not really far from Belgium to the Netherlands, who studied pendulum clocks in the 17th century. We have a stable solution, oscillating solution, so a system of multiple oscillators that can be neurons or the myocardium cells or uterus cells during contraction, whose dynamics is synchronous. They move all together. Sometimes the coupling can bring this oscillator to lose their synchronization. So here the objective is to keep the system synchronized, so to have a stable state. Is opposite as in the case of Turing instability. Those two phenomena have been studied on networks, on many different kinds of networks, but we are studying it on a quite recent concept that is emerging in network science, that of non-normal networks. A network is non-normal when its adjacency matrix is non-normal. So namely, it doesn't commute with its adjoint. And this is an example of non-normal network, is a directed acyclic network, but there are many others. And non-normality was already known to have effects on the dynamics. For example, in linear systems, if a network, if the matrix governing the dynamics is strongly non-normal, we can observe a transient dynamics, so this transient growth. Then the system being linear, if the system was stable, we go back to the stable state. But still, we have this transient growth that when the system is nonlinear may actually bring the system to a new basin of attraction. So we are on a stable state, we perturb, we should remain in that state, but non-normality and this transient growth bring the system away from the equilibrium into a new equilibrium. And it has been studied in the last years because it was found in Namur by our group, not me, but our group, that most of real-world networks, from food webs, neural networks, genetic networks, and so on, are non-normal. And most of the times they are strongly non-normal. So in this paper, they are described the parameters to measure non-normality, and most of the real-world networks are non-normal. The reason for this transient growth and for this sensibility to perturbation is given by the theory of pseudospectra. So for a non-normal matrix or operator, because this theory was always studied in the framework of hydrodynamics, not just in networks, a non-normal matrix is more sensible to perturbation. So its pseudospectrum is bigger if compared to a normal analogous. So we have two results, one for pattern formation and one for synchronization. Last year, we published a work about Turing pattern formation. We have our master stability function that I showed you at the beginning of this presentation that is negative in the case of non-normal network. So we should be stable. We perturb the stable fixed point and we should go back to the stable equilibrium. But you see this transient growth at the end results in a pattern. And we can give an explanation. So even though we are unstable, we are stable, after the perturbation we go unstable. And we can show that the pseudo spectrum, so the perturbed spectrum, the perturbed master stability function, goes unstable even though the actual, so the master stability function that we can compute stays negative. In the framework of synchronization, we are working on something that should come out on the archive very soon. So the preprint is almost ready. We studied the Brussellator in an oscillatory regime, so in a limit cycle regime, on this kind of network. And this network is very interesting because it's non-normal. It's the simplest non-normal network that you can find, but its spectrum is real. So if we compute the master stability function in a setting in which it should be stable, we see that actually the discrete master stability function stays stable. But then if we integrate the equation, we see that the perturbation amplifies and then goes through all the nodes and then breaks the oscillations, resulting in an inhomogeneous pattern. And if we compute the pseudo spectrum, we see that for the order of magnitude of perturbations that we use, it actually goes in the area where the Lyapunov exponent is positive. So again, the non-normality breaks the stability. Moreover, if we send epsilon to 0, obtaining the maximum non-normality, here we took a measure, a classic measure of non-normality, it's called the Enrici index. We see that the smaller epsilon is, and the more the pseudo spectrum, so the pseudo master stability function, goes into the instability region. And this is important because in the field of synchronization, in the literature, usually we look for network enhancing synchronization. And this is one example of network enhancing synchronization. However, when non-normality is involved, classical tools such as the master stability function do not capture this effect a priori. You have to integrate the equation to see these effects. And so you need to, so you don't see the non-normality, and you miss the fact that even though the network seems to be very good to enhance synchronization, then in the end, it amplifies the perturbations, leading in a loss of synchronization. So we need to look for a trade-off between networks that are optimal for synchronization, accounting for non-normality. So, and I concluded. Before finishing, I would like to thank my supervisor, Teo Carletti, and Malbor Aslani, Dr. Aslani from University of Limerick, who was involved with me and Teo in both works. And then for the first work on Turing pattern formation, Philippe Maini from Oxford and Lucio Fanelli from Florence. And for this work on synchronization, James Gleason from Limerick. And I would like to thank our funding sources, in particular the Walloon region, who is paying for my PhD scholarship. And I thank you for your attention.